March 1940. Britain finds itself in a stranglehold, not from bombs raining down on London or tanks rolling across the countryside, but from a more insidious threat: the silent disappearance of ships in the frigid, dark waters of the Atlantic Ocean. Week after week, convoys depart North American ports laden with vital supplies like food, fuel, medicine, and raw materials, but fewer and fewer vessels make the return journey. The numbers paint a harrowing picture. In the first 4 months of 1940, German U-boats have sent over 250 Allied ships to the ocean floor. This is not just a statistic on a naval chart, but a tragedy representing thousands of lives. The United Kingdom relies heavily on imported supplies to sustain its population, with around 55 million tons of goods arriving annually. However, the nation's self-sufficiency in food production is limited, accounting for only 30% of its needs. This precarious situation means that without the vital maritime convoys, the country could face the prospect of starvation within a matter of months. Commanding the German U-boat fleet, Admiral Karl Donitz has honed a formidable tactic known as the Wolfpack. This strategy involves coordinated attacks by groups of submarines, overwhelming the escort vessels protecting the convoys. The U-boat submarines do not engage in conventional warfare, preferring to strike at night and surface to launch their assaults under the cover of darkness, where the British forces are at a disadvantage. The Asdich 115 sonar system proved incapable of detecting the enemy's presence. A single 117 torpedo could swiftly sink a 10,000-ton freighter 120 within minutes. If fortunate, the 122 crew might have just enough time to abandon ship before 124 the freezing Atlantic waters claimed them. 126 British convoy commodores faced impossible 128 dilemmas with each voyage. They could sail faster 131 and leave the slower merchant vessels 133 behind, or zigzag to evade torpedoes, but 136 burned precious fuel in the process. Sticking together 138 for protection presented a larger target. 141 Every decision carried life or death consequences 143 for hundreds of men. Winston Churchill 145 who assumed the role of Prime Minister in May 1940, 148 would later reflect that the U-boat peril 150 was the sole threat that truly 151 unnerved him. The looming threat of Nazi invasion, the devastating Blitz, and the fall of France weighed heavily on the British psyche during the war. Yet, it was the silent hunters prowling beneath the waves that truly haunted the nation's leader. By the spring of 1940, Britain's merchant fleet was dwindling at a rate that outpaced the shipyard's ability to replace it. The Royal Navy, stretched to its limits, struggled to escort convoys, hunt for enemy submarines, and defend the homeland all at once. Destroyer captains, racing from one convoy to the next, were running their ships into the ground, as there were never enough escorts to go around. Some convoys crossed the seas with only 1 or 2 warships protecting a fleet of 30 or more merchant vessels. The German U-boats have become increasingly bold in their tactics, operating in coordinated groups known as wolfpacks. During the day, a single U-boat would shadow a merchant convoy, relaying its position to the rest of the pack. Then, under the cover of night, 5 or 6 submarines would converge for a devastating attack. British sailors have dubbed this period the happy time, though for the Allies, it's been a nightmare. But the Wolfpack assaults are just one of the challenges facing Churchill and the British Admiralty, who must also contend with the growing threat of the German submarine force as a whole. On November 21, 1939, the British destroyer HMS Gypsy was navigating the Tempomys estuary, just off the English coast. This was not enemy territory, but rather a channel the Royal Navy had thoroughly swept for mines on numerous occasions. Suddenly, a massive explosion ripped through the ship's hull, causing the Gypsy to sink within minutes. There was no torpedo wake, no periscope sighting, and no warning whatsoever. 3 days later, a similar incident occurred. This time, the threat was not a pack-hunting predator, nor did it require a crew. It struck without warning in areas where ships should have been completely safe. This unseen menace was a lone, 304 killer lurking in the waters. The SS Terryuni Maru merchant ship exploded at 3:42, followed by another at 3:45 in the same vicinity. The explosions continued, with ships blowing up in harbors, river mouths, and coastal waters that should have been completely safe by 3:49. The blasts were catastrophic, ripping off entire bows, breaking vessels in half, and instantly killing the crews by 3:56. By early December 1939, over a dozen ships had been lost in British home waters, leaving Admiralty baffled. These were not torpedo attacks, as there was no evidence of submarine activity in the shallow, heavily patrolled areas. The explosions were also not caused by traditional contact mines, as British minesweepers had repeatedly combed the routes. Merchant vessels plying the seas found themselves in a perilous predicament. Vessels were simply sailing along, minding their own business, when suddenly they would vanish in a violent eruption of water and twisted wreckage. This unseen menace sowed panic throughout British shipping. Captains who had fearlessly faced German U-boats in the Atlantic now trembled at the prospect of entering their own ports. With a U-boat, they knew what they were up against. They could employ evasive maneuvers, deploy escorts, and drop depth charges. But this new threat was like fighting a ghost. Crews began referring to the mysterious phenomenon as the death trap, and some merchant captains flatly refused to sail through certain channels, even under direct orders. The British naval forces endured mounting losses throughout December 1939 and into January 1940. The mighty battleship HMS Nelson, a 45,000-ton symbol of British naval might, strikes something off the coast of Scotland and barely limps into port with her bow nearly destroyed. If even these capital ships are not safe, then no vessel is secure. Britain's harbors are becoming graveyards, and the Royal Navy remains baffled by the mysterious forces sinking their ships. Then, a breakthrough occurs on November 23, 1939, just 2 days after the sinking of HMS Gypsy. A German aircraft is spotted dropping something by parachute into the mudflats near Schubis at low tide. As the tide recedes, British bomb disposal experts cautiously approach the drop site. What they discover will provide a critical clue in unraveling the mystery. The Royal Navy's encounter with an unprecedented mine discovery proved a harrowing experience. Lieutenant Commander John Uvey and his team meticulously examined the mysterious device, aware that a single misstep could prove catastrophic. As the tide rose around them, they worked against the clock, their findings ultimately sending shockwaves through the Admiral's office. This mine, unlike any seen before, required no physical contact to detonate, a chilling revelation that would forever transform naval warfare. Concealed within the casing lies a far more sinister element, a magnetic sensor that detects the metallic hulls of passing vessels. When a ship sails overhead, the mine senses the magnetic field of the steel and iron, then detonates. The Germans have weaponized the very principles of physics. Suddenly, the shallow water attacks, harbor explosions, and minesweepers sailing unharmed make chilling sense. Britain is no longer battling just submarines, but an invisible enemy that transforms every ship's metal hull into a death sentence. The captured magnetic mine lands on the desk of a man who has no. The Royal Navy's desperate scramble to mobilize every available brain against the Nazi threat led to the creation of the Department of Miscellaneous Weapons Development in late 1939. This unconventional department became a haven for unorthodox ideas and the individuals who proposed them. Canadian chemistry professor Charles Good, who had come to Britain on an academic fellowship before the war, found himself swept up in this effort, despite having no prior military or naval experience. When the magnetic mine problem reached Good's office in early 1940, most experts were stumped. However, this scientist, unencumbered by traditional naval thinking, approached the challenge with a fresh perspective. Leveraging his scientific expertise, Good began exploring innovative solutions to this pressing issue, determined to contribute his unique skills to the nation's wartime efforts. Seasoned naval officers are approaching the challenge through conventional means. They propose constructing sturdier mine sweepers and reinforcing hull plating. Meticulously mapping minefields is also on the agenda. These are sensible, logical tactics from experienced seafarers. However, one individual perceives the issue from a radically different angle. He grasps a fundamental truth that eludes the admirals. This is not merely a naval problem, but a matter of physics. The mind does not concern itself with armor thickness or ship design. It responds to magnetic fields. Every vessel is essentially a giant magnet drifting through the water. During construction, the steel components become magnetized due to the hammering, welding, and shaping processes that align the iron molecules with the Earth's magnetic field. Even after the vessel's launch ushers in a distinctive 813 magnetic signature, which unfortunately proves fatal for the crew. Goodeve's proposed solution, though initially sounding outlandish, holds the key to addressing this issue. The plan involves wrapping the entire 822 ship in electrical cables and powering them with onboard generators, creating an 831 electromagnetic field that would effectively cancel out the vessel's natural magnetism, rendering it magnetically 837 invisible. This revolutionary idea, however, faces skepticism from seasoned naval officers, who are hesitant to heed the advice of a university professor on matters they have grappled with for decades. The naval engineer, Goodeve, proposes a revolutionary concept to render warships invisible to magnetic detection. Challenging the skepticism of his peers, he meticulously explains the underlying physics. Every vessel's hull generates a magnetic field, which can be neutralized by producing an equal and opposite field around it. This principle, akin to noise-canceling headphones, effectively masks the ship's presence from magnetic sensors. Though initially met with doubt, Goodeve's calculations demonstrate the feasibility of this cloaking technology, potentially allowing vessels to evade magnetic-triggered weapons. The proposal to demagnetize the entire British naval fleet was an ambitious and unprecedented undertaking. 928 The challenge was that no one had ever attempted this on a scale larger than a small rowboat. 931 Goodeve, the engineer behind the plan, had devised a technical solution known as DES, a unit of magnetic field strength. 935 However, the logistics of applying this method to the thousands of vessels in the British fleet, from battleships to cargo ships, were staggering. 941 Each ship would require custom calculations, precise wire placement, and careful calibration. 949 Britain simply did not have the time to implement this complex process, as ships were being sunk daily by the magnetic mines spreading throughout the major shipping channels around the British Isles. 1001 The threat posed by the German U-boats sinking merchant vessels in open water was becoming increasingly dire. The Earth's magnetic properties have become a critical factor in the ongoing naval conflict. With ships unable to safely reach their destinations, the Royal Navy finds itself in a precarious situation. Despite the skepticism and the immense scale of the challenge, Admiral T reluctantly grants Goodeve permission to pursue a seemingly unconventional solution. Faced with limited options, the military leadership recognizes that in times of war, even the most audacious ideas must be considered. The magnetic mine, a deceptively simple yet ingenious device, capitalizes on the Earth's own magnetic field. With the North and South poles acting as the planet's natural magnets, the mine's design cleverly exploits this fundamental property of the environment. The construction of a ship in Earth's magnetic field causes the iron molecules in the steel to align themselves, resulting in the vessel becoming permanently magnetized. This magnetic signature is most pronounced at the bow and stern, where the hull curves most dramatically. Even a 10,000-ton cargo ship can generate a magnetic field strong enough to be detected from a distance of 30 feet. The magnetic signature is particularly significant for larger vessels, such as battleships with their substantial steel armor. The process of building a ship, from hammering steel plates to welding joints and bending metal into shape, takes place within the Earth's magnetic field. This exposure causes the iron molecules in the steel to gradually align themselves, much like tiny compass needles, all pointing in the same direction. Consequently, the ship becomes permanently magnetized, carrying a distinct magnetic signature. This magnetic signature is strongest at the ends of the hull, the bow and stern, where the curvature is most pronounced. A typical 10,000-ton cargo ship can create a magnetic field strong enough to be detected from as far as 30 feet away. The magnetic signature becomes even more pronounced in larger vessels, such as battleships, which possess massive steel armor. The ship's magnetic signature remains a constant presence, radiating from its hull like a beacon that could trigger any nearby magnetic mines. German engineers fully grasped this principle when designing their weapon. Resting silently on the seafloor, the mine conceals a magnetometer, a sensitive compass that monitors the ambient magnetic field. As a vessel passes overhead, the magnetometer senses the abrupt shift in field strength. Once this change exceeds a predetermined threshold, an electrical circuit closes, allowing current to flow and detonate the explosive charge. The magnetic field never dissipates, even when the crew has departed. It persists through fog, darkness, and all other conditions, consistently emitting a signal that could activate the mine's triggering mechanism. This unwavering magnetic signature is a fundamental aspect that German innovators carefully accounted for in their mine's design. The seafloor transforms into a deadly zone as a detonator and 650 pounds of high explosive detonate. From Germany's perspective, the ingenious design is virtually undetectable. Conventional mines float on the surface or just beneath, attached to anchors by cables. Mine sweepers can sever those cables or detonate the mines with gunfire. But magnetic mines rest directly on the seafloor in shallow waters. Mine sweepers sailing overhead trigger them like any other vessel. Britain lost several minesweepers before realizing what was happening. Goodeve's Degaussing solution tackles the problem at its core. If you can't, concealing a vessel's magnetic signature necessitates neutralizing its magnetic field. This is achieved by wrapping the ship in a lengthy cable loop, sometimes encircling the entire hull, or employing multiple loops at varying heights. When an electrical current flows through this cable, it generates its own magnetic field. Adhering to the principles discovered by physicist Hans Christian Ørsted in 1820, the key is ensuring the polarity is correct. If the ship's hull has a magnetic north pole at the bow, the current must be directed through the cable to create a south pole at the same location. The interaction between these two magnetic fields effectively cancels out the vessel's overall magnetic signature. Every vessel possesses a unique magnetic signature, which can be influenced by various factors such as the steel composition, construction techniques, age, and even the orientation during construction. Consequently, a one-size-fits-all approach to magnetic signature mitigation is ineffective. Instead, each ship requires individual assessment and customized solutions to effectively reduce its magnetic profile and evade detection by magnetic mines. The intensity of a ship's magnetic signature can range significantly, from as high as 30 feet to as low as a few inches, depending on the specific characteristics of the vessel. Properly implementing the appropriate countermeasures around the entire hull is crucial to achieving the desired reduction in magnetic signature and ensuring the ship's safe passage. The task at hand was to transform the original text while preserving all factual content. The goal was to achieve a structural difference of 50 to 55% from the original. Here is the paraphrased text. Facing a daunting challenge, Good embarks on a mission to revolutionize ship construction procedures for the entire British merchant and naval fleet. With a tight timeline of mere weeks, he must find a solution that can be implemented swiftly. In January 1940, the first test takes place at HMS Vernon, the Royal Navy's torpedo and mining school in Portsmouth. Good and his team select a small minesweeper, HMS Board, as their experimental subject. Over the course of 3 days, they meticulously measure the ship's magnetic field from every angle, utilizing sensitive magnetometers borrowed from university physics departments. Afterward, they meticulously wrap 2,000 feet of heavy electrical cable around the vessel. The crew meticulously drills a carefully calculated pattern of holes. 1436 connects them to a generator, and activates the switch. The 1439 results are astonishing. The ship's 1440 magnetic signature plummets by over 90%. 1443 when they sail the HMS over test 1445 magnetic sensors. The instruments barely 1448 register any readings. It's as if the ship 1450 has disappeared from the magnetic spectrum. 1452 Goodeve's outlandish concept actually succeeds. 1455 But triumph breeds its own nightmare. 1458 One test vessel is a proof of principle. 1500 Britain operates over 9,000 merchant 1502 ships, plus hundreds of Royal Navy 1505 warships, destroyers, cruisers, 1507 battleships, and countless auxiliary 1509 craft. Every single one requires demagnetization if 1512 they're to survive passage. The steady stream of ships entering British waters never ceases, with American freighters, Canadian escorts, requisitioned trawlers, and emergency-built cargo vessels arriving daily. Calculating the sheer scale of this maritime traffic fills Good with dread. Each vessel requires approximately 2,000 feet of thick copper cable, amounting to over 18 million feet for the merchant fleet alone, enough to encircle the Earth's equator. This staggering demand places an immense strain on Britain's already stretched copper supplies, which are essential for supporting electrical infrastructure, munitions production, and aircraft manufacturing. Goodeve now faces the challenge of establishing an entirely new supply chain solely for procuring this critical cabling. Moreover, the installation process presents a significant logistical hurdle, as the task cannot be entrusted to just any electrician off the street. The precise placement of the cable is crucial for this task. Improper positioning could prevent the degaussing field from effectively cancelling the hull's magnetism. Applying too much current risks starting fires or damaging electrical systems, while too little current leaves the ship vulnerable. Each installation requires trained personnel with expertise in both electrical engineering and naval architecture. However, Britain faces a shortage of such specialized individuals, as the country is engaged in a multi-front war effort. Every qualified engineer is already working long hours on critical projects like radar, aircraft engines, and gun systems. To address this challenge, the country must rapidly create an entire team of degaussing specialists, train them in a matter of weeks, and deploy them to shipyards across Britain and eventually overseas. Across the globe, a network of allied ports is established to combat the magnetic mine threat. The Admiralty spearheads the initiative, rapidly deploying degaussing stations at key maritime hubs like Portsmouth, Liverpool, Glasgow, Belfast, and Cardiff. Each station is equipped with magnetometers, cable supplies, and hastily trained technical crews. Upon arrival, ships undergo immediate magnetic measurement and degaussing procedures. Cables are wound around the hull, and generators are installed to generate the necessary degaussing current. The entire process is designed to be completed within 48 hours, but the reality on the ground is far more complex. Vessels often arrive at port already damaged from attacks, necessitating repairs before degaussing can even commence. Shipments of critical cable supplies face delays, and generators frequently malfunction. Measurement errors by the crews further complicate matters, forcing them to restart the process. Amidst these logistical challenges, the relentless hunt for submarines continues. In the spring of 1940, British naval forces faced a daunting challenge. Vessels were forced to wait outside harbors for hours, 1720 to 1722, before joining convoys bound for the Atlantic. Recognizing the urgent need for a quicker solution, 1724 Good and his team developed a simplified system called wiping. 1729 This innovative approach involved ships slowly passing by a shoreline installation, 1734 where powerful electromagnets temporarily neutralized their magnetic fields. 1736 While not as permanent as proper demagnetization, 1740 the effects lasted several weeks. 1742 Wiping stations were quickly established at harbor entrances, 1745 enabling the processing of multiple ships per day, 1747 a significant improvement over the previous rate of one every 1750 days. By March 1940, Britain had gained the upper hand, 1754 degaussing vessels faster than Germany could lay 1755 magnetic mines. However, the race against time remained desperate. 1758. The transformation of the small experimental program known as Operation Dazzle into the largest crash engineering project in British history during World War II was a remarkable feat. By April 1940, degaussing stations were operating around the clock, with 3 shifts working 24 hours a day, 7 days a week. Sparks flew from welding torches at midnight, and exhausted electricians measured magnetic fields at dawn. Cable crews worked through air raids, ignoring the sirens, as every hour a ship sat waiting for degaussing was an hour it couldn't carry desperately needed supplies. The Admiralty pulled workers from anywhere they could find them, even calling back retired electricians and recruiting university physics students to meet the urgent demand. The wartime degaussing effort mobilized a diverse workforce, drawing personnel from all walks of life. Women joined the crews in unprecedented numbers, operating specialized equipment like magnetometers and calculating intricate cable patterns. This work, which demanded precision and mathematical aptitude rather than physical strength, became a critical component of the nationwide degaussing operations. By the summer of 1940, over 3,000 individuals were engaged in these vital activities across Britain. The logistical challenges were immense. Massive reels of cable arrived by the ton at ports, and workers developed specialized techniques for handling the heavy, thumb-thick copper wire that weighed several pounds per foot. Lowering crews on scaffolding along the ship's hulls, they secured the cable with brackets every few feet, meticulously ensuring its proper installation. The installation of waterproof and corrosion-resistant connections on a large freighter is a laborious process, taking an entire day of grueling physical work. After the installation, each ship must undergo rigorous testing to verify its magnetic signature. The vessels slowly navigate designated testing areas while onshore magnetometers record their readings. If the measurements remain too high, the crews must return and make adjustments, such as modifying the current, repositioning cables, and troubleshooting the system. Some ships require multiple attempts before they are properly neutralized. The program extends beyond British shores, with Canada establishing demagnetization stations in Halifax and Montreal. American ports, while technically neutral, also participate in this process. Until December 1941, a covert operation quietly established demagnetization facilities for ships that would join British convoys. From Gibraltar to Alexandria, Cape Town to Bombay, wherever Allied shipping concentrated, the demagnetization equipment and personnel followed. Eve's team diligently wrote training manuals, and the specialized gear was shipped overseas to train foreign crews in the necessary techniques. Yet the losses continued to mount. June 1940 brought catastrophe on multiple fronts. France's fall to Germany granted the Axis access to Atlantic ports like Brest and Lorient, cutting 450 miles off the German submarines' hunting range. Suddenly, the U-boats could remain on patrol much longer, striking convoys farther from British shores. And while thousands of ships now had demagnetization protection against magnetic mines, the Admiralty confronts arduous triage decisions as the fleet remains vulnerable to torpedoes in open waters. Prioritizing warships for degaussing or newer vessels over older ships with years of service, the commander must weigh factors like speed and cargo capacity. Each choice entails risks, with some ships waiting longer and facing heightened danger. Despite the Blitz's devastation of London's docks and Liverpool's catastrophic May 1941 bombardment, which claimed over 2,000 civilian lives and battered port infrastructure, the degaussing operations in Glasgow, Belfast, and other critical hubs persist. Cardiff endures air raids while cable crews continue wrapping ships around the clock. By the end of 1940, Britain has degaussed over 4,000 vessels. That number exceeds 10,000 by mid-1941, an engineering achievement rivaling the construction of the ships themselves. Yet, this is accomplished under wartime conditions with limited resources, constant enemy action, and the knowledge that every delay costs lives at sea. The numbers speak volumes. In the first 3 months of 1940, before degaussing became widespread, magnetic mines sink or damage 115 British ships in home waters. By late 1940, after thousands of vessels received degaussing, The British naval forces faced a formidable challenge in the early years of World War II as Germany's magnetic mines threatened to cripple their merchant fleet. However, a daring and innovative solution emerged that would ultimately neutralize this wonder weapon. By 1941, the number of ships lost to magnetic mines had dwindled to negligible levels, a testament to the effectiveness of this countermeasure. Yet, the peril of the Atlantic remained, as the relentless Wolfpack attacks continued to take a heavy toll on the convoys. Despite the success in combating the magnetic mines, the convoy war entered its most brutal phase, with the German U-boats inflicting devastating losses on the Allied shipping. In the winter of 1941, the German U-boats unleashed a devastating campaign against Allied shipping. During this period, the U-boats sank an astonishing 62 vessels totaling over 300,000 tons. However, the implementation of the convoy system provided a much-needed sense of predictability for merchant captains. Prior to this, ships had to navigate a treacherous gauntlet, facing threats from multiple directions, including magnetic mines in shallow waters and air attacks near coastlines. The journey from North American ports to Britain was fraught with peril, with no safe zones along the route. The adoption of the convoy system eliminated one variable, allowing escort commanders to focus solely on the U-boat threat. This meant they no longer had to worry about ships exploding in harbor approaches, and vessels could take evasive action with greater confidence. The convoy system, though not a panacea, gave merchant captains a much-needed sense of security and predictability in the face of the U-boat's terrifying efficiency. The British maritime forces can now focus their defensive resources, including destroyers, aircraft, and radar stations, solely on anti-submarine warfare, rather than scattering them across multiple threats. This strategic shift has a significant psychological impact on merchant crews, who previously witnessed ships explode in supposedly safe harbors. Now, they have confidence that their vessels can safely reach port, boosting morale and reducing crew refusal of assignments. The steady drumbeat of mysterious explosions that terrorized British shipping in late 1939 and early 1940 has come to a halt. While ships still sink, crews at least understand the nature of the threat they face. The demagnetization program had become a routine part of naval operations by 1942. With every vessel receiving the treatment as automatically as they were painted. New ships were constructed with demagnetization coils already installed in the hull. Liberty ships were rolling off American production lines at an astounding rate of 3 per day, all equipped with demagnetization systems as standard. What had seemed impossible in January 1940, protecting the entire Allied fleet, had become standard operating procedure just 2 years later. The Germans tried to adapt to this development, modifying their magnetic mines with more sensitive triggers in an attempt to detect even demagnetized ships. They also added acoustic sensors that responded to propeller noises, but the Allies' demagnetization efforts had become an integral and unexceptional part of naval warfare by this point. The magnetic mines that nearly crippled British maritime trade in 1940 were a formidable challenge, but the ingenious countermeasures developed by the Royal Navy ultimately prevailed. The combination of magnetic and pressure detonators required both a specific magnetic signature and a pressure wave from the ship's bow to trigger the explosives. However, each new mine adaptation necessitated fresh production and deployment, allowing Britain's minesweepers to become increasingly effective at clearing the waters. The Battle of the Atlantic raged on until Germany's surrender in May 1945, with U-boats remaining a deadly threat throughout. Yet the magnetic mine menace that had nearly paralyzed British shipping never fully recovered, thanks to the success of Goodeve's solution. Merchant vessels continued to cross the Atlantic, sustaining Britain's supply lines and war effort, not because they were invincible, but because the Royal Navy's countermeasures had turned the tide. The unsung hero of maritime safety, Charles Goode, made a pivotal contribution during World War II that went largely unrecognized. While the codebreakers at Bletchley Park and radar scientists at Bawdsey Manor received post-war acclaim, Goode's groundbreaking work in ship degaussing remained obscure outside naval engineering circles. His innovation, which saved thousands of vessels and countless lives, exemplifies how the most impactful wartime advancements can occur quietly, overshadowed by the more publicized exploits of battles and generals. Degaussing would go on to become a permanent fixture of naval doctrine for major powers, underscoring the far-reaching significance of Good's little-known achievement. The modern naval landscape is dominated by sophisticated computer-controlled demagnetization systems that continuously adapt to shifting magnetic conditions. Submarines, which must evade detection by magnetic anomaly sensors, employ even more advanced demagnetization technology. These same principles also safeguard undersea cables, scientific instruments, and sensitive electronics from magnetic interference. Good's broader impact lies in his unconventional approach, as he thought like a scientist rather than a naval officer bound by tradition. He recognized that modern warfare increasingly meant grappling with the laws of physics, with radar transforming air combat into an electromagnetic chess match. The advent of sonar had transformed submarine warfare into a battle of sound waves, while the weaponization of Earth's magnetic field had engaged the minds of military strategists. Victory would hinge on the ability to comprehend and exploit scientific principles. The Royal Navy recognized this shift, and the Department of Miscellaneous Weapons Development, where Good worked, evolved into a permanent institution. Britain forged closer ties between universities and military research, integrating scientists into the core of defense planning. Good himself ascended to become Director of Naval Land Equipment and subsequently the Controller of Research and Development for the Ministry of Supply. After the war, he was honored with a knighthood. The Royal Navy, an organization steeped in centuries of traditions and protocols, faced a critical juncture during the tumultuous events of 1940. When conventional methods proved inadequate in the face of an existential threat, the Admiralty took a bold step. He entrusted a university professor with a revolutionary idea, granting this individual the authority to overhaul the entire fleet. This remarkable display of institutional courage and flexibility enabled Britain to achieve remarkable accomplishments in less than 2 years, despite the immense challenges it confronted. The professor, who continued working on 27 scientific problems until his death in 1980, had been given the opportunity to challenge the Navy's deeply rooted customs and procedures. This flexibility under pressure, a rare quality in such a tradition-bound organization, allowed for the implementation of innovative solutions that proved pivotal in the nation's struggle. The narrative underscores the importance of adaptability and the willingness to embrace unconventional approaches, even within the most rigid of institutions. This lesson serves as a testament to the transformative power of visionary leadership and the ability to overcome entrenched norms in the pursuit of critical objectives. The concept proved its effectiveness, scaling to thousands of ships, training thousands of workers, and establishing a global infrastructure. This essentially solved a problem that threatened to starve the nation into surrender. All while fighting a war on multiple fronts, enduring bombing raids, facing possible invasion, and operating under conditions of absolute desperation, the convoys kept sailing. Britain survived, and though degaussing was just one factor among many, crucial tactics like convoy operations, escort carriers, long-range patrol aircraft, and sheer courage all played pivotal roles. This eliminated one deadly threat at precisely the moment when Britain couldn't afford any more losses. In war, sometimes the smallest innovations can have the greatest impact. The most unconventional approach often proves to be the optimal solution. Encasing vessels in extensive electrical wiring and transforming them into powerful electromagnets can unexpectedly safeguard a nation. Moreover, the true hero may not be the commanding officer or the airborne aviator, but rather a Canadian academic specializing in the principles of magnetism, whose expertise surpassed common expectations.